Today we will finish up chapter 1. We'll talk about electron configuration, and then we will do chapter 2. These guys on this slide here, these are the geometries of orbitals. Orbitals are where electrons live. This is the lowest energy, these are the highest energy orbitals. And basically each of these can hold 2 electrons. And the regions of space that the electrons can occupy are shown. But before we do any of this, in case you missed the Academic Success Center, they do tutoring, and they're fairly good. Most students like it. They're in A100. Here's an email address, whatever. Any questions? One thing I wanted to point out, when you go to Blackboard, I hope you can all see tutorial 1 by now. If you can't, remember you need to go to Lab Safety and click on the safety contract link. Then it's visible. What I wanted to point out was this guy, Review Videos. These are little videos I made a few years ago that basically are 5 to 7 minutes long, and they cover one subject. So you click on that. These are the ones for chapter 1. Again, they're 5 to 7 minutes, one subject. If you click on significant figures, you'll get this. This is 7 minutes, okay. 7.5. And there's Nemo in case you were looking for him. Any questions? All right. Electron configuration. When we were talking about isotopes in chapter 1, we looked at this rendition of a carbon atom. At the time, I pointed out that I had placed the electrons in 2 different energy levels. The inner electrons here are called the core electrons. They're not involved in making bonds or anything like that. They're closest to the nucleus, and they're just there. These higher energy electrons are called valence electrons. These are the ones that we're going to use to make bonds. We'll do that in chapter 3. The purpose of talking about electron configuration, which is usually a general chemistry sort of subject, is to make sure you understand where valence electrons come from and how to figure just how many you're dealing with. When we look at the periodic table, we said we divided this into groups going this way and periods going down. Carbon has 2 energy levels because it's in the second period. The number of electrons that can exist in any one period is given by this little formula, 2n squared, which means that the first period can accommodate 2 electrons. The second one, we can put in 8. The third, we're up to 18. Then we get 32, 50, whatever. Now, within these energy levels, the electrons will live in these orbitals. The orbitals are called S, P, D, and F. This is the lowest energy of all of them. This is an S orbital. It's a sphere. It's round. And it can hold 2 electrons. That's it. After you put 2 electrons in the S orbital, if you still have leftover electrons, you can put them in what are called the p orbitals. Again, the regions of space that the electrons can occupy are shown by the colors. Now, it's easy to look at this and say, okay, 2 electrons, I can do that, 1, 2. Not the way it works. Quantum mechanics tells us that we have no clue where in this space the electrons are. The only thing we know is that they're never ever in the middle. Called a node. Once you fill up the p orbitals with 2 electrons each, total of 6, the d orbitals come next. They're an interesting assortment. Once again, each one can hold 2 electrons. This with the inner tube is one of my favorites. Finally, once we fill up D's, we can do F's. We have 1, 2, 3, 4, 5, 6, 7 F's, and they're very interesting geometries. But again, each of these only holds 2 electrons. Any question on the concept? So let's go back to the periodic table here. In our periodic table, in the first period, we have 2 elements, hydrogen and helium. The electrons here go in the lowest energy, which is the 1 with the period s orbital. 1 electron goes here, the second one goes here. When we go to the second period, the first 2 electrons will go into the 2s orbital. Once we fill that one, we bump over to here, and the next 6 electrons go in the 2p orbitals. Third looks very much like the second. First 2 electrons go into 3s. Next 6 go into 3p's. Now, if you're paying attention, and I hope you are, this is supposed to have 18 orbitals, isn't it? Well, it does, but there's a little bit of a twist. Turns out that the energy level of the 3Ds here is slightly above the 4s. So we have to fill it first, then we fill up the 3Ds. So for the fourth period, we do this. First 2 go here. The next 10 go here in the 3D orbitals. And finally, we fill up the p orbitals. Putting this in total context of the periodic table, so you can actually understand why it looks like this. This is 1s, 2s, 2p, 3s, 3p, 4s, 3d, blah, blah, blah. Just the way the orbitals fill. Now, in this class, we are going to deal only with the first 3 periods. So I won't ask you for anything that has d orbitals. We'll talk about d orbitals, but we're not going to use them in terms of configuration. Any questions? Well, let's do a simple problem then. Go back to our friend carbon. Second period, atomic number 6, it has 6 electrons, right? It has 6 electrons. 2 of these will fill up the first quantum level of 1. The next 4 will be in the second. These 4, the higher energies in the second, are our valence electrons. So, here is carbon. That means that the 1s is completely filled. We write it like this: 1 for the period, s for the orbital, 2 electrons. The 2s will also be completely filled. We write that 2 2s2. And the two p orbitals here will have 2 electrons. We simply write that as 2p2. Again, these guys right here, these 4, are the valence electrons. If I asked you to write the full electron configuration, you would do this. 1s2, 2s2, 2p2. It's pretty straightforward, isn't it? But quantum mechanics has a habit of always throwing in something strange, and it does. The quantum description of an electron gives it 4 properties. The first 3 describe the orbitals that the electrons go in. The second is called spin. Now, the electron really isn't a little ball that's spinning, but it behaves as if it was. Because it's charged and has this property of spin, it generates a magnetic field. That magnetic field can be oriented up or down. We show little arrows up and down. Now, basically, we're not going to do a whole lot of the up and down arrow things, but it's nice to understand where they come from. What this tells us from Hund's rule is that when we are filling orbitals, like the p orbitals, what you do is you put 1 electron in each orbital first, and they will all have the same spin. So they'll all be up, for example. If we have more electrons, we put them in one at a time with the opposite spin. This would represent 3 full p orbitals, 1 up, 1 down in both. Okay. If we were doing hydrogen and we wanted to show electrons with their spins, hydrogen, first period, 1 electron. We would show it simply as a spin either up or down. If we go all the way over to helium, we're going to add 1 more electron to the s orbital. It must be added down. 1s1, 1s2. Now, the nomenclature that we're going to do on exams is simply going to be 1s1, 1s2, blah, blah, blah. Okay? We're not going to do the up and downs on exams. But it might help you with the tutorials. One more problem here. Fluorine, second period, atomic number 9. Let's do its electron configuration using spins. Again, atomic number 9, 9 electrons. The first quantum level will be filled. The next 7 electrons will go in the second. The 7 electrons are the valence electrons, so always the highest energy. So, here is fluorine. That means the 1s is filled, so we'll do 1s with 2 electrons, 1 up, 1 down. The 2s is also filled. In the 2 p's, we have 1, 2, 3, 4, 1, 2, 3, 4, 5 electrons. Sorry. We have 5 electrons in the 3p orbitals. So the first thing we would do is put 1 electron in each orbital, and then we would pair them up until we use up all 5. the configuration would be this, but on an exam, this is what you would write. Any questions? Well, speaking of an exam questions. Electron configuration for sulfur. Now you look at your periodic table. Sulfur is here in the third period. Right here. That means that the first period is full. The second period, the s orbital is full. The p orbitals for our second period are also full. The third period, the s orbital is full. And finally, we have 1, 2, 3, 4 electrons in the p orbitals. So which of these is right? 1s2, 2s2, 2p6, 3s2, 3p4. Another test question. This one turned out to be a little trickier than I wanted, but still a decent question, I think. Lithium, atomic number 3. Number of electrons in the highest energy shell is what? Well, lithium is here. That means the first level is full, right? The second level has 1. What's the highest energy electron? It'll be in the second level. 1 in the 2s2 orbital. The valence here is 1. There's a tutorial for this, of course. Let's do sulfur again, because we know the answer. Sulfur is still right here. That means the 1s is completely filled. So we show that by putting the number 2 here. The 2s will be completely filled. Put another 2. Now for the 2 p's in this one, we have 3 slots. They're going to be 6 electrons because it's full. But we want to realize that these are 3 sets of 2, like that. The 3s, that's full. And the 3p, we have 1, 2, 3, 4. So we would start off with 1 each, and then we would change this to a 2. On an exam, once again, this is what you would write. Now, Blackboard is slightly different. You don't have to do the 2, 2, 2. You do 6. Looks something like this. Let's do magnesium. Magnesium is over here in the third period. That means the 1s is full, right there. The 2s is full. The 2p has 6 of them. And the 3s has 2. So, on Blackboard, you would enter this as 2 in the 1s, 2 in the 2s, 6 in the 2p, that's different. The 3s will have 2. Now, here's a slot for 3p. Blackboard will not let you have an open field. So if you have an open unused field, you must enter a 0. Got it? All right, that basically does electron configuration. Again, the highest energy electrons, they'll be in the highest period. Those are the valence electrons that we'll use for bonding. All right, let's move on to physical and chemical properties of matter. We said matter was defined as anything that occupies space and has mass. Elements, the simplest form, contains only one type of atom. Compound. The notion of a compound is new. If we take two or more atoms, we can link them together and we can make what's called a compound. The linking together is always in a specific and constant patterns. There are two types of compounds we're going to deal with, mostly in chapter 3. This is methane, carbon in the middle, 4 hydrogens around. Every methane looks exactly like this. Same geometry, same everything. That's what the specific pattern means. The electrons between the carbon and the hydrogen here are shared. This is called a molecular compound where we have sharing of electrons. The other type of compound, this is sodium chloride. In sodium chloride, we don't share electrons. The sodium atom totally transfers its electrons from sodium to chlorine. Because sodium is missing an electron, it's positive. Chlorine has an extra, so it's negative. This is called an ionic compound. This is just an endless array, if you will, of these plus and minuses held together electrostatically. So two types of compounds, molecular, where we share, and ionic, where we don't. Now, pure substances. Pure substance contains only one type of matter. So it'll be either an element or a compound. A mixture is a combination of pure substances. Mixtures come in two forms. Heterogeneous, that means different, and homogeneous, which means the same. If we look at a selection of gravel, this is gravel on the beach in St. John, Virgin Islands. I took the picture. The test here to show that this is a heterogeneous mixture is simply the sample. If I go and I take a handful of rocks from here, they will be totally different than a handful of rocks from here. Different samples, heterogeneous. So while I was doing this, I also had a beaker with me, and I took a little beaker full of salt water. If you think about salt water, it's basically water with salts dissolved in it, mostly sodium chloride, a lot of magnesium, whatever. This is a homogeneous mixture. We know that because if we take a sample from here and a sample from here, they are absolutely identical. We know it's a mixture because if we let this sit out, the water will evaporate, go through the water vapor, leaving the salt behind, and we're left with that. So we get it back just by the simple thing of evaporation. It's a mixture and it's homogeneous. Let's do a couple silly ones here. This is a rock. Is a rock a pure substance? Well, you could say it's pure rock. It is. But if we take a little chip of this and then cut a very thin section, put it under a microscope, we see something like this. The rock is actually an aggregate. Sample sizes. If we take a sample here, totally different composition than the sample here. So the rock is a heterogeneous mixture, just squeezed together. These are gold bars. As I look at them, they're all different, aren't they? Are these gold bars a pure substance? Well, they are, because they meet the definition of being an element. If you look at this on the atomic level, it's simply an array of gold atoms. It's a pure substance. This is sodium chloride under a microscope, table salt. Little cubes, they all look different, but these guys are nothing but the compound sodium chloride. It's a compound, meets the definition, pure substance. Any questions? All right, let's do another set. Think about these. I'll hush for a second. Air, ground pepper, seawater, sugar, gasoline, and gravel. Now we're all very familiar with air. What is air? Air is actually mostly nitrogen, about 20–21% oxygen, and then little slivers of other things, methane, CO2, whatever. This clearly represents a mixture, doesn't it? But do our sample. If I take a sample from this side of the room and a sample from this, they're the same. Therefore, this is a homogeneous mixture. Ground pepper. If you wanted to, you could put this under a microscope and you could, with little teeny tiny tweezers, separate these into gray, white, black pieces, couldn't you? Sample size, if we took a sample here, it would be mostly tan. Here is mostly blacks. This is a heterogeneous mixture. We've done seawater. Seawater, again, the sample test. Sample here, sample there. It is nothing but salts dissolved in water, homogeneous mixture. Sugar, ever thought about sugar? Table sugar looks like this. This is a molecular model. On Wednesday, we're going to build a couple of these in lab. The blacks here represent carbon atoms. The reds are hydrogen or oxygens, and the whites and grays are hydrogen. There are two rings here that are joined together. Every molecule of table sugar, sucrose it's called, looks exactly like this. This is a chemical compound. It meets the criteria for being a pure substance. Ever thought about exactly what gasoline is? Well, should, I guess, looks something like this. It's an organic compound. It's a mixture of organic compounds. Aromatics like benzenes, substituted benzenes, alkanes, cycloalkane, branched alkanes. It's a mixture of all of these guys. And yet, the first stuff out of the pump is going to have one set composition, and the last stuff out will have the same composition. Therefore, this is homogeneous. And finally, gravel, well, we did gravel too. Gravel is just a bunch of little rocks. Any questions? All right. Physical properties and states of matter. Physical properties include things like appearance, density, melting, boiling point, refractive index. It's descriptive. It's a descriptive thing. Chemical properties will describe the way something reacts with something else. Physical properties. You can take a substance and make it undergo a physical change. Now, the test here is it still the same substance? We start off with a solid, ice. It melts. We get liquid water. Finally, this can evaporate and form a gas. But they're all still water. It's a physical change. We can show our three states of matter this way. This represents a solid, that's a liquid, and this represents a gas. In a solid, the particles are basically motionless. Well, they do sit and shake, but because nothing is ever still, with children, but they sit and shake, but they cannot move relative to each other. It's a lump. In a liquid, we put enough energy in that these individual particles can now slip and slide over each other. But they still can't quite get away. Because of that, this is a liquid, takes on the shape of its container. And a gas, we now put enough energy in that we have no attractive force between the particles. These are flying around till they hit the walls or each other. This represents a gas. Solids define shapes and volume. Liquids define volume, but they take on whatever shape. And gases have neither defined or whatever. They just take on shape and volume of the container. We can go from solid to liquid by putting in energy. It's called melting. This will happen at a defined temperature, called a melting point. Every pure substance that we know of has a unique melting point. That's because these guys are held together by attractive forces. We'll talk about these in the kinetic molecular theory, but the attractive forces are unique for every substance. So the energy necessary to overcome them is also unique. If we have a liquid, we can go to a gas. That's the boiling point, again a unique temperature. Solids, we can also go directly from the solid to a gas called sublimation. Most commonly we see this in the reverse direction. This is where frost comes from. Frost comes from water vapor going directly to crystals of ice. All right, here's a simple problem. This is a vial containing bromine. Bromine melts at minus 7.2 centigrade and boils at 58.8. Bromine is here on the periodic table, group 7. It's a very toxic substance. In this little vial, we have bromine gas. That's the yellow in the background. We have bromine in solid phase, the crystals here, and this little bit of liquid at the bottom, some that is melted, that's liquid bromine. Okay, so if I ask you, if we're at minus 20, what's the physical state of bromine? Well, minus 20 is awfully cold. The melting point is minus 7. So if we're below minus 7, it's a solid. If we're at 80, well, the stuff boils about 58, 59. We're above that. This is the point where it changes from a liquid to a gas, so it's in the gas phase. If we're at minus 0.12, okay, that's around zero-ish, isn't it? At minus 7, it freezes. At 60, it boils. This is in between the two. This is liquid. Now, this is a fairly simple concept, okay? Sometimes when you write an exam, you like to play games with people's minds. And one of the games is to give them a question that you know everybody's going to get right, because it makes you feel good, okay? Gives you confidence. So, I put this question on an exam once. Pure substance, 15 degrees above its boiling point. Is it solid, liquid, or gas? Everybody's going to get this right? Almost nobody got it right. I was astounded. So, I made some slides and we talked about it the next class period. The simplest way to do this is to think about it in terms of a phase line. Solid, liquid, and gas, right? Melting point, boiling point. If we're 15 above the boiling point here, we're somewhere here. It's a gas. So after explaining it this way, the next year I put a similar question on. Melts at 115, boils at 325, at 25, what is it? People did better this time. Solid, liquid, and gas. Here's our melting point, here's the boiling point. We're at 25. That's way down here. It's a solid. One more. Negative numbers. Everybody hates those. It melts at minus 45, boils at 4, at minus 36. What is it? Melting point, boiling point. We're at 4 degrees. I'm sorry. We're at minus 36 here. It's in a liquid. Very simple problems. Just work on the concept. Any questions? All right, I mentioned the kinetic molecular theory. One of the basic tenets of the kinetic molecular theory is that everything in this universe has an inherent attraction to everything else. If we reduce the temperature enough, everything would glom together. Think of buckyballs. Remember those? Buckyballs were little magnets. Actually, you can buy them again. They were taken off the market because little kids thought they were so neat. They ate them, and of course, messed up their insides, killed some kids even. Think of the magnetism as the attractive force. This would represent a solid. Now, this is a little computer simulation. This is a solid, and this guy has energy. We're going to shoot it at it. The little balls are going to bounce everywhere, off each other, off the walls, and then slowly, every time they hit the walls, they will be losing a little bit of energy. So, what happens is they will slow down, and eventually they'll stick together. Let's go. Boom. This is an actual calculation for each of the little balls. And you can already see, as they're losing energy, they're starting to attract each other. There's another pair pairing up, looking for partners. And if we allow this to run long enough, these will all glom together into one little cluster again. Kinetic molecular theory, everything has an attractive force to everything else. All right. Again, this represents a solid. In a solid, we don't have enough energy to overcome this attractive force. So the best they can do is just sit there and vibrate. If we start putting energy in, we will reach a magic point where the energy we put in is enough to just overcome the attractive force, and we get our liquid. Again, they don't have enough energy to go up into the gas phase, but they're slipping and sliding everywhere. If we put in even more energy at some magic point, we will totally break the attractive forces, and we wind up with a gas. So the things we want to remember about the states of matter. A gas, particles are highly separated. That's why you can compress a gas. The attractive forces are minimal. It takes on the shape and volume of its container. The liquid, or closely spaced, is not compressible. Has a defined volume, but takes on the shape of the container. And finally, a solid is just a lump. Relatively fixed positions, it is not compressible and has a defined shape. Solids, liquids, and gases. All right. Another physical property that we want to deal with is going to be density. I said physical properties are basically appearance and other physical things. This is mercury. It's a liquid at room temperature. It's a metal. Mercury used to be so fun to play with. Sadly, they won't let us play with it anymore. It turns out it has a very strong tendency to form vapor. That vapor is a neurotoxin. Makes you stupid. Okay. Density. Density is another physical property. Now we're going to do a full lab on density. It is defined simply as the mass of a substance, typically expressed in grams, divided by the volume, typically expressed in cubic centimeters. But this can be any unit of mass, this can be any unit of volume. Remember, a cubic centimeter looks like this. Cubic centimeter is the same as a milliliter, exactly the same. If we had exactly 1 cubic centimeter of gold, something like this, 1 centimeter on the side. That thing would weigh 19.3 grams. So we can calculate its density. Mass divided by volume. Our mass is 19.3. Our volume is 1 cubic centimeter. The density is 19.3 grams / cubic centimeter. Any questions? Simple concept. Look at some other substances. Water, pretty close to 1. Many people think it is 1. It isn't unless you're at 4 degrees centigrade. Then it is exactly 1. Sulfur or mercury, 13.5. Again, we used to play with it. It's fun. Yeah. Sulfur, about 2. Iron, almost 8. Helium and oxygen are gases. Their density is just very small numbers. Typically, when you have a gas, instead of grams per cubic centimeter, you do grams per liter. Makes it more reasonable numbers. Simply multiply by 1,000 to get there. Now, you're going to see something in this next little clip that's kind of strange. There's a guy, he's not strange, and this is a pool of mercury. We hope he's holding his breath, but what he is holding is a cannonball. He is going to take the cannonball and toss it into the pool of mercury. Now, cannonballs are pretty heavy, aren't they? But by George, it floats. How about that? Why does it float? The density of mercury, 13.5. Iron for the cannonball is about 8. The less dense thing, in this case, the cannonball, floats on the mercury. Now, going back to the late 60s, National Geographic was doing a spread on making hats, I believe. Mercury is used for making hats, hence the Mad Hatter. Okay. They were taking pictures at the mercury plant. Mercury is very dense, cannonballs can float on it, so can you. So they asked one of the guys to just go and sit on the little puddle of mercury. And he did. Unfortunately, if you look at the guys, it looks like he's kind of already been exposed to the vapors, hasn't he? They realized this at National Geographic after they had published the picture. People complained. They bought up every copy they could find. But I still got the picture. All right, simple problem. We have 250 cubic centimeters of a gas. It weighs 0.45 grams. What is the density? Well, you think to yourself, okay, I can do this. Density, mass per unit volume. We know a volume. We know a mass. All we have to do is divide these to get density. Mass divided by volume. Our mass is 0.45 grams. Our volume is 250 cubic centimeters. We simply do the division, and we get 0.0018 grams / cubic centimeter. Sorry, I thought something else was coming. Grams per cubic centimeter. Any questions? All right, well, we are going to do this next one sort of in lab. It's historic. You are given a rock, but you're not really given a rock, you're given a rubber stopper. And you're asked to determine its density. We know density is mass divided by volume. You can weigh it and get the mass. But how do you get the volume? Well, Greek scholar Archimedes, so a long time ago, was given a crown from the king. And the king wanted to know if it was pure gold or if somebody skipped on it. Well, he could weigh it and get the mass. But how in the world do you take a crown and figure out the volume? You could melt it down and make a cube, but you can't do that for a crown, really. So, the story goes that one day, as a Greek, he was taking a bath. The tub was filled with water, climbed in, and the water poured over the sides. Made a mess. He said, quote, "Eureka!" Jumped out of the tub. Eureka means, oh my goodness, I think I got it. Jumped out of the tub, ran through the streets naked, screaming, "Eureka!" Okay. Basically, he discovered that in order to find the volume, you can measure the volume of a liquid that it displaces. So we're going to do this with our rock. We know the mass is 43 grams. We have a little cylinder here. We measure this initial volume at 22.5 mils. We're going to drop the rock in there gently. When we do, it displaces a liquid, and the volume rises to 45.6. The difference, 45.6 minus 22.5, is the volume of our rock. Mass divided by volume, 43. Simply the difference here gives the volume. That's 23.1 mils, which is the same as cubic centimeters, remember. Do our simple division. 1.86 grams per cubic centimeter. Sometimes, instead of the slash, you will see grams, centimeter, minus 3. Same thing. Sometimes, or we could also express this as grams per milliliter. But it's a solid rock. Typically, centimeter is what you want. Any questions? Well, what happened with Archimedes and the king? Turns out that it was filled with lead, and the density was off, and they killed the goldsmith. Sorry, don't mess with the king. Ethanol, organic alcohol. Density is 0.79. What's the mass of 15 cubic centimeters? So, density is a simple ratio, isn't it? It's mass divided by volume. That's a ratio. I want to solve this using given, ratio, and find. Here, we are given the ratio, 0.79 grams divided by centimeters. Here is our given, 15 cubic centimeters of our ethanol. given 15 cubic centimeters, our ratio 0.79 over 1 centimeters in the denominator, and we're finding grams. As our given, the ratio is set up with centimeters in our denominator. Cubic centimeters will cancel. Simply multiply it out. We get 11.8 grams. Our given, our ratio, and what we're trying to find. All right, well, we did significant figures last chapter, didn't we? These are measurements. Are the significant figures right? Here we have 4. Here we have 3. Here we have 3. What about the 1? That's actually referred to as an exact number. It's a definition sort of thing, not a measurement. So, yes, this doesn't count, and 3 is proper. Do another one. Mercury again, 13.5. We have 999 grams. What is the volume? Our given is going to be 999 grams. Our ratio is simply the density. Set it up. Now we see there's a problem here right away. Given has units of grams, and this, our ratio is in the numerator. Has to be upside down, doesn't it? What you do in a case like this is simply flip it over. So our given, take the ratio here. We want to turn it over. There, that's better. Now grams cancel, and we're multiply 1 by 999 divided by 13.5. We have about 74 mils. One more simple one here. We have 2 liquids. They are immiscible, means they don't mix. Think oil and water. Liquid A has a density of 0.985, B is 0.873. When you put them together, what happens? Which liquid will rise to the top? The 2 liquids don't mix. The word for that is immiscible. The thing with the lowest density will float. Remember the cannonball. Lowest density floats on the heavy density. Now this is a simple exercise that's kind of like real life in lab. We're doing a reaction. Acetone is one of our reactants. We need 2 grams of acetone. We know its density. What volume do we need? Again, density is a ratio. Solve it using this. Our given is our 200 grams. We need to flip this ratio over. Our given is 2 grams. Here's our density. We know we have to flip it over to find cubic centimeters. Start with our given. Flip it over so grams are in the denominator. And simply multiply and divide. 2.5 cubic centimeters. Because it's a liquid, we would typically do 2.5 milliliters. All right, on your first hour exam, I can guarantee you, you will be doing problems for density. So let's look at some from the archive. Substance has a mass of 93, density of 14.6. What's the volume? Now we're going to do this 2 ways. You can do either one on the exams. We have a formula. Density is mass divided by volume, right? We're looking for volume. We could plug density in, plug mass in, and solve for volume. Volume is going to be our mass divided by our density. Simply do our division, and we get our answer. We can also do this using give and find ratio. That's our given. Here's our ratio. Flip it upside down, multiply it out, 63.7. That's a liter. Remember, 1,000 cubic centimeters in a liter. Any questions? Another one. We're looking for the mass. We have 51 milliliters, and here's our density. Let's do this with given ratio find. Our given is our volume. This is our ratio. Cubic centimeter and mil are the same thing, so that works. It's our given, there's our ratio, cancel it out, multiply, we get our mass. We can also do this with the formula. Looking for mass, substitute in, density divided by volume gives us 74.24. So, what's the answer? Nothing turned yellow, did it? We have 74.24, that's the same as that. And 74.2, which is it? 0.2. 3 significant figures, 3 significant figures. That's the answer. Density interconversions. We're looking for the density. Well, remember, it can be any unit of mass divided by any unit of volume. So here we want kilograms and milliliters. Our volume is 1.57 mils. And our mass, oh my goodness, is given in milligrams. What we're going to have to do is change milligrams to grams and grams to kilograms. Divide by our volume, and we get the answer. Our density is mass divided by volume. Here's our mass in milligrams. Here's our volume. 8,000 milligrams is the, well, okay, So I did the division here. Our answer in milligrams per mil is 5687. Divide by 1,000, that's 5.8 grams per mil. To get that to kilograms, we have to divide by another 1,000, 0.0569. Simple metric conversions. All right, there are two tutorials. One that everybody loves and one that nobody loves, except me. But they're the same, okay? I call this density 1. It's a table. You will randomly get numbers in some squares. All you have to do is plug in the third one. Here we are given a mass and a volume. Remember that density is simply mass divided by volume. 24.8 divided by 18, that's all you have to do. And we're at 1.37. Here the volume is missing, but we have mass and density. Density is mass divided by volume, so volume is mass divided by density. Simple algebra. Substitute in 96 divided by 1.87, 51. Here we're missing mass. We know volume, we know density. Mass is going to be density multiplied by volume. Density multiplied by volume is mass. Simply multiply the two guys together, 54.7, and we are correct. This is density 1, and again, everybody loves it. Blackboard looks just like this. Density 2 is the same as density 1, except no table. It's a word problem. And you have to do at least one metric conversion. So, looking for a volume in cubic centimeters. We have a mass in kilograms. Our density, 2.3 grams per mil. Now, mil in cubic centimeters, that's fine. They're the same. We have to convert our grams or kilograms to grams. Our mass was given in kilograms. Multiply it by 1,000, we get grams. We're looking for the volume. We are given the density. Mass divided by density gives us volume. Substitute. 15 divided by 2.3, 6.52. And you're right. So once again, one metric conversion, and it's a word problem. Let's do one more. Let's see. Looking for the density in milligrams per mil. We have a volume in liters, so we have to divide this by 1,000. And we have a mass in grams, not milligrams. So this one actually has two metric conversions. Our mass, 33 grams. Okay. Our volume starts off as 0.15 multiplied by 1,000, 15 cubic centimeters. We want our density. We're going to simply, density is mass divided by volume. Mass divided by volume, this gives us a density in grams. But we want this in milligrams per mil. Have to simply multiply it by 1,000. 2213. Any question? Everybody loves density 1, nobody loves density 2. But density 2 are more sophisticated problems. Again, blackboard looks just like this. Any questions? All right. Physical and chemical properties. We've done this. Physical properties, a fixed characteristic, how it looks, how it smells, whatever. State, color, odor, hardness. Chemical property tells us how a material reacts with something else. Physical change, thing that denotes a physical change, you still have the same substance. It's just different somehow. Chemical change, you get an entirely new substance. Here's a reaction that we'll see over and over again. This is a little vial containing bromine. Again, bromine is here. It's a halogen, very toxic, very high vapor pressure. So this is bromine gas, this is liquid in the bottom. This is aluminum. What we're going to do is take aluminum foil and add it to bromine. Now aluminum is a metal, conducts electricity, conducts heat well. Bromine is a diatomic molecule. They're covalently bonded here. Here's our setup. We have a little beaker with some bromine in the bottom. Here we have aluminum foil. We will take and add the foil to the bromine. Now I don't recommend doing this on the lab bench because remember this is toxic vapor. It sits down there for a second and then you see fire and you see huge plumes of toxic gas being released. But when it's all over, see this crust at the top? That's the new chemical substance that we made. This is aluminum bromide, a white solid. So, a liquid, solid metal, we wind up with a compound that is a white solid. In chemistry, we will refer to this as a chemical reaction. We will link reactants and products with an arrow. Any questions? All right, that was a chemical change. Physical change, again, are melting icicles. Solid water becomes liquid, becomes gas, but it's still water. Same substance. However, if we take water and run electricity through it, we can do a chemical change and break water down into hydrogen gas and oxygen gas. This is a chemical change. All right. As I said, reactants go to products. The arrow here is a special arrow for chemistry. It has the same properties as an equal sign. That means you must have the same numbers and types of atoms on both sides, and also the same masses. Here's a reaction. K is potassium, we all know that. This is two hydrogens bonded to oxygen, that's water. This is potassium hydroxide, OH, and this is hydrogen gas. The little S stands for solid. L is liquid. AQ means it's dissolved in water, aqueous, and G is gas. Bottom line, what this equation tells us is that if we take potassium, add it to water, we will get potassium hydroxide and hydrogen gas. But remember how when we added the aluminum to the bromine, we saw a fire because it got hot. In this case, the heat will cause the potassium to melt, then it will cause it to burn as it reacts with oxygen. Let's look at it. This is water. This is potassium metal. It's under oil. Otherwise, it would react with the air. And we're going to take our tweezers, put a little bit in, and watch what happens. Hook out a little chunk. Soon as it hits, you see it's melted, bouncing around. As the hydrogen is produced, it burns off. Really fun reaction to do. If you use a chunk that's too big, it will explode. Don't want that to happen. The hydrogen reacting with oxygen. We said it burned, right? Let's look at that one. Hydrogen reacted with the oxygen. It was already hot to give water. Now this is a balloon filled with hydrogen. This is a room filled with oxygen, 20% or so. This is a flaming stick with somebody standing out here that's brave. Definitely evidence of a chemical reaction. This is why people become chemists. They love doing stuff like that. Any questions? Are these chemical or physical changes? Gold bar hammered into gold leaf. And you're done. It's still gold, isn't it? It's just thin. Physical. Water heated to boiling. Well, it's water transforming into the gas phase, but it's still water. Physical. Carbon, charcoal, burned in oxygen, forming CO2. That is chemical. New substance is formed. Any questions? All right. When I said the reaction arrow had the properties of an equal sign, I said same numbers and types of atoms on both sides, right? Also the same mass on both sides. This is the law of conservation of mass. This was not evident to chemists in the old days because, you know, you get fire and stuff like that. You got to be losing mass, they thought. Well, you're wrong. It was Lavoisier, a French chemist, who demonstrated the conservation of mass. This guy was actually, for his day, was quite brilliant. What he did was he took mercury. If you heat mercury and oxygen, you get mercury 2 oxide. If you then take your mercury oxide, heat it up again, you can go back and make mercury. Drive the oxygen off. Here's the equation: mercury plus oxygen, mercury 2 oxide, mercury 2 oxide, mercury and oxygen. What he did was to put the stuff in one spot, heat it up, boil it over, and weigh it carefully. And he demonstrated mass of reactants equals the mass of the products. For its day, this was stunning. It really was. Sadly, this day happened to be the time of the French Revolution. And that's what Lavoisier and his lovely wife looked like. They, unfortunately, were nobility. The French Revolution did not like nobility. They immediately arrested him, threw him in jail. The world, the science world, objected seriously. You don't let the guy go. He's smart. The judge at his trial said, quote, "The Republic, that's France, needs neither scientists nor chemists." And so they could have set off. Maybe this is what's wrong with France now. Who knows? All right, let's look at some more problems. Which is a physical change? Lighting a match, sugar and tea, melting of aspirin. Yes, aspirin is a substance, and it melts. When you light a match, what happens? It burns, doesn't it? You get gas forming, you get ash forming. Sugar and tea is still sugar dissolved in tea. Aspirin, whether it's melted or not, is still aspirin. B and C are physical. Which of these are chemical properties of carbon? It's a solid. It's insoluble in water. Dissolves in carbon tetrachloride. Reacts with oxygen. Crystallizes to give diamonds. Well, we're looking for chemical properties, right? New substance. This still is just a physical characteristic. This is a physical characteristic, and so is this. Diamond is nothing more than carbon reacting with oxygen is a chemical property. Which of the following is correct? Compounds cannot be decomposed into elements? Nope, that's wrong. Okay? Compounds can be decomposed, you just have to put energy in. Elements and compounds are pure substances. That sounds good, actually. Elements but not compounds? That's silly. B is a correct answer. Now let's do one last one here. Cadmium, copper, and zinc have densities of 8.6, 8.9, 7.1. We have an unknown metal that's one of these guys. 15 cubic centimeters, here's its mass. What is the metal? Just like Archimedes, what you have to do is calculate the density. Once you calculate the density, you can identify the metal. Mass divided by volume gives 8.92. That's the middle guy. We're at copper. All right, thus endeth chapter 2. Today, we did electron configuration and density 1 and 2. We now have 1, 2, 3, 4, 5, 6, 7, 8 tutorials, 40 points for you. Don't let them get away. You must have all the tutorials done by the time we sit down to take the first hour exam. Okay? Automatically they disappear. Any questions? All right, guys, I hope the recording worked this time. Didn't work last time. Think I got it fixed. So if you need to check it, you can check it online. Have a good day. On Wednesday, we will do Lab 1. Bring your goggles. Okay? Bring your goggles on Wednesday. Also print the procedure for Lab 1. You have to hand in the last page at the end of lab. Yeah.
We have to buy these goggles?
You have to buy. Sorry. One sec. Yeah.